Okay, thank you for inviting me to this very stimulating session, and I'd also like to acknowledge my co-author on this work, Taka Ito. We've had a lot of fun working on this particular project. So basically what we are doing is we're trying to figure out if we can say anything about the Atlantic Circumpolar Current and the strength of the Atlantic Circumpolar Current during the last glacial. And our approach is to look at the density structure across the circumpolar current. As you can see, those surfaces of constant density tilt strongly up towards the Antarctic margin. And first, we explored the relationship between the Antarctic Circumpolar Current and the density structure in the modern observations, and also in the PMIP2 LGM model runs. And then we'll look at some of the data constraints that we have on LGM seawater density across the Atlantic Circumpolar Currents, and finally we'll try to take a stab at an estimate of the change in ACC strength during the LGM. So first, just looking at the modern data, the Atlantic Circumpolar Current is largely baroclinic, meaning that if we calculate the transport using just the density gradients and assuming a small bottom velocity at the bottom, we get very nearly to the actual total transport. On the right-hand panel is looking at this baroclinic transport, this time looking only at the density on either side of the circumpolar current, so near the Antarctic margin and also near the margin south of Australia, and also only looking at the density contrast above 3 kilometers. So this would be the baroclinic transport relative to 3 kilometers water depth. And we can see that there's a very good relationship between the actual at ACC transport and the baroclinic ACC transport above 3 kilometers water depth, both for the modern and LGM model simulations, and also for the modern data, which is in the purple star there. So what are our data constraints for the last glacial maximum? So our best kind of data constraint for density is pore water data, because from pore water data we can get directly at last glacial maximum salinity, and we can get at temperature by looking at the O18 change in the pore water and in nearby benthic foraminifera. So we're going to use a pore water profile that was published previously in Adkins 2002 from the Chatham Rise, which samples lower circumpolar deep water near to where we're going to be assessing the density gradient. We also are going to use oxygen isotope data in benthic foraminifera, both in a group of sediment cores located in that red box south of Australia, and also from a few sediment cores located in the Antarctic zone, some of which are south of the Antarctic Circumpolar Current. So first, looking at the pore water data, we're going to use the Site 1123 pore water reconstruction off of New Zealand. And we can see that the salinity that's reconstructed is about 36.1 PSU, and that is now very well supported by a number of recently published salinity pore water measurements from the deep Pacific from a variety of water depths. That was published by Insua et al. Just this year. So we believe that the oxygen isotopes in benthic foraminifera can also help us to constrain past density. Part of this is because the O18 in the foraminifera is a function of the temperature of calcification. It's also a function of the O18 of the seawater in which they calcify. And in the warm surface ocean, the O18 of the seawater is well related to salinity, although this relationship gets complicated in areas where sea ice can form. So we have to also get some more direct measurements of salinity for deep waters. So here are the O18 of benthic foraminifera. In the left-hand panel is for the Holocene. These are for the solid red dots, or for the cores off of Australia. All of these cores are taken from the literature. The open circles are the cores that are in the Antarctic zone, some of which that are south of the Antarctic Circumpolar Current. On the right-hand side are the LGM O18 data. They're shifted towards heavier values because of the whole ocean changes in O18, but broadly the structure is similar. Okay, well, how do we go from these O18 profiles to density? Well, I'm not going to go into the gory details, because if I do, I won't finish on time. But basically, I'll give you a flavor for the types of constraints that we wrap into our analysis. So the first thing we do is we acknowledge that along the Antarctic margin today, we can think of three main water masses that are controlling the temperature, salinity, and O18. And those would be the circumpolar deep water, Antarctic intermediate water, and then surface waters in the region. So first we're going to try to constrain the temperature and salinity of these end members, and also the O18, because that will help us translate these temperature and salinity measurements that help us translate the O18 of calcite measurements into temperature and salinity. So for the lower circumpolar deep water end members, we can just use the pore water-based reconstructions from Adkins et al. 2002, and we do that. For the surface and Antarctic intermediate water end members, we have to bring we don't have pore water data, so we have to be a little bit more creative. For the surface, we'll use temperature from Paleo-sea surface temperature proxies in the region. For the Antarctic intermediate water temperature, we look both at the temperature in the formation areas of Antarctic intermediate water, and also some very limited data that is directly assessing Antarctic intermediate water temperatures. We then also have to think about what the relationship between the O18 of seawater and salinity might be for Antarctic intermediate waters and surface waters, and so we make some estimates of what that relationship is today and how it might change under glacial conditions. So finally, once we've determined the TS and O18 of seawater of these M members, we can then use the O18 calcite data to basically interpolate between these M member values and build our density profile along the Australian margin. For the Antarctic margin, it gets a little bit more tricky. We don't have any pore water data along the Antarctic margin, so we don't have any independent constraint on salinity on the Antarctic margin. What we are doing in this analysis is we're using the lower circumpolar deep water density from north of the ACC, and we're assuming that is the same density along the Antarctic margin. And that's quite a big leap. It's the kind of leap a theoretician would make. So let's look at this leap and see if it really is going to give us an answer that makes any sense. So here we have what we've done is, again, we've taken the PMIP, LGM, and modern ACC, and we've looked at how well we can capture the Baroclinic ACC using this estimate that the Antarctic margin is the same as is the same density as a lower circumpolar deep water. And the relationship is not nearly so beautiful as those that I've shown you before, but we still basically get a positive correlation, which is good. So we think we can say something using these lower circumpolar deep water to estimate what the density might be like on the Antarctic margin. So when we put all this together and estimate the LGM Baroclinic ACC transport, we find that it is reduced by about 20%, but with an error of about plus or minus 20%. And this error is determined using a Monte Carlo error estimate, varying all of the assumptions that we put in to mostly into translating those oxygen isotope data into density estimates. We can say, well, we don't really know much of anything about Last Glacial Maximum ACC transport, or we can say, well, there's an 80% probability that it was lower or similar to today. And we also can say with some confidence that that when we make the assumptions we do, it wasn't, twice what it is today or anything like that. This transport estimate is, well, it's sensitive to the estimate to the assumption we make about the Antarctic margin density values, but it's also the Monte Carlo error estimate is most sensitive to uncertainty in the Antarctic intermediate water temperature and also the O18 of the lower circumpolar deep water. So not too much changed, but perhaps a little bit weaker ACC is consistent with the picture that Nick McCabe published earlier this year based on sortable silt, showing not much change in the near bottom energy in the Drake Passage. One thing that Taka has been looking at is when we looked at these PMIP LGM models, he noticed that many of the models that show an increase in ACC transport also show an increase in the strength of the lower cell of the overturning circulation, so stronger Antarctic bottom water formation. And conversely, the LGM PMIP models that show a weaker ACC transport tend to show a weaker Antarctic bottom water circulation. So this is an interesting area that we are now exploring. So because my light is yellow now, I'm just going to leave up my conclusions, but I will highlight this last conclusion, is that we could do a much, much better job here if we had pore water-based temperature and salinity estimates in a lot of different places, and especially on the Antarctic margin. So I hope that happens someday.
Thank you very much, Jean. We have time for questions.
So the question is, are there some mechanisms for why LGM ACC would be weaker? One mechanism that people talk a lot about are shifts in the westerly wind belt, so maybe northward shifts, which would decrease the wind energy over the ACC. Extending sea ice further to the north might do something.
So, Jean, the final Baroclinic transport estimate you got was fairly uncertain, but were there any depth levels where you could constrain density better than other depth levels?
I think our best constraints based on the data right now are that lower circumpolar deep water density, right? But because we don't have an equivalent density estimate on the Antarctic margin, and we're just assuming that that's what the density is on the Antarctic margin. There's no depth where we have good constraints across both sides, I guess, that would be any better than any other. And I should say in response to Lou's question, another reason for weaker ACC transport is that if we're looking at the transport south of Australia, we actually not only have this kind of wind-driven ACC that's going clear around the Antarctic, but we also have this kind of, if you look at the red arrows going around Antarctica, there's kind of an extra amount of ACC flow that goes south of Australia, around Australia, that goes south of Australia. So you'll notice there's 157 spheredrops going south of Australia relative to 140. And today, the subtropical front passes south of Australia, and it appears from other paleo data that it does not do that during the LGM. So that's a way also of reducing the ACC flow.
One quick last question.
Yeah. Following up on this set of questions, I mean, the theoretical evidence is that actually you should not expect much of a change in transport in the ACC because of these effects of saturation. I mean, talking about changes in winds doesn't get you very far because generally there is an eddy activity that compensates them. You're talking about a 20% change, which is what, 20 sverdrup out of 140. Mm-hmm. That seems to me, isn't it more consistent with the idea that probably it's a strong constraint that the ACC transport didn't change consistent with what expectations are. And you're never going to get it probably better than that. Even today, models cannot reproduce the transport of the ACC to within 20%.
Yeah, so there are theoretical considerations that would suggest that it can't change by very much. That being said, there are plenty of LGM model runs for which it changes by a whole lot, right? So you could say that the fact that it doesn't change by a whole lot, that it doesn't double, gives some comfort to the theoretical idea that it can't change by very much. Certainly within the errors, you could say it didn't change at all, right? But it certainly didn't double. So the theoreticians should feel good.